you very much for the introduction, Trey. And really, it's a great pleasure to come to the Perceive 2020 conference to talk about our work in deep learning for visual inspection. Um, so, um, so one of the things that you may have heard about is Industry 4.0. So, what are the key technologies in Industry 4.0? The analytics and intelligence is a very important part. So if you think about analytics and intelligence, what's really happening now is deep learning. And there's a analyst report by Tractica that estimate deep learning software will be growing at 39.3% CAGR and to $60 billion in 2025. So this represents the fastest growing technology in artificial intelligence. So we have been working on deep learning based computer vision for the last essentially since deep learning was kind of starting to show the great promise that it has. And it has very wide applications in automating visual inspection for quality control and analytics-driven process improvement in digital manufacturing. And we have also been looking at some of the other applications. One of the applications we have also looked at is how is deep learning used in creative workflow? And I'll show a couple of examples at the end of the presentation. Another key component in Industry 4.0 that's really exciting for us in HP is the advanced production methods, such as additive manufacturing and, for example, 3D printing. And so the combination of analytics and intelligence with technologies like 3D printing is also a really, really big opportunity that we see in the future. So, and on the left, these are some of the things in the digital transformation of the industry, like, for example, artificial intelligence, industrial IoT, big data and analytics, robotics, and the 3D printing. And what does it mean? What does this mean? How are these technologies going to transform the manufacturing industry? What we see is that this will really result in very rapid innovation. People can make things and see it work very much immediately, shorter time to market. People don't have to store a lot of things. You can make things and you can use it right away. So that will result in less storage space, more efficient supply chains, higher capital efficiency. So, so one of HP customers, for example, in Spain, is creating custom dolls, and so let me show a video that will show you how it works. So, so this company makes dolls, and you can see they have been, the company has been in this area for since 1940, so it's a very, very old company. And one of the dreams of the kids of when they own dolls is that they want the dolls to look like them. And through the traditional manufacturing process, you have a mold, and then you make the doll, the same doll, many times. But with HP's 3D printing technology, multi-jet fusion, they can essentially make custom dolls. So here you see that they take pictures of the kid, and then they create a 3D model of the face. And now they can essentially create the head, the doll's head, that's entirely customized, and the doll's head will look like the kid. So so now through this digital manufacturing process, we can do essentially mass customization. And now the kid, you can see she got a doll that really looks like her. And so she's really, really happy about it. So this is really exciting. And this is essentially what the digital manufacturing can deliver. So so let me go back and talk about some of the opportunities for AI and the deep learning. So one of the things that's really important is when we look at the factory quality control process, quality control really needs to happen throughout the whole manufacturing process. So here we show that we get components from the supplier. So we need to make sure, we need to inspect and make sure that the components are all functioning without visual defects. And then the components need to be assembled, and then we need to make sure that the assembly is correct, and then it becomes a product, and then it's packaged, and then we need to make sure that the package is also done correctly and there's no damage in the package, and the label of the product matches what's in the package. So throughout this process, we essentially need to observe with a camera, and then make sure that we use computer vision to inspect, and then make sure all these processes are done correctly. The product has no defect. And then we feed that into the big data analytics. So if there's a defect, then we use computer vision to figure out what defect it is, and then we feed it into the overall big data analytics pipeline, and then we drive the process automation. So essentially what we need to do then is to figure out what caused the defect, and then change the manufacturing process so that we reduce or eliminate that defect. And so at HP Labs, we have been looking at research in all these areas, 2D printing, 3D printing, and manufacturing. And if we look at these areas, what's kind of really interesting is that in manufacturing, typically we manufacture a lot of the same part many times. So when we do the inspection, the product image of this one particular part is relatively similar to the product image of the next part that's inspected. And that is not really true for 2D printing and the 3D printing, because more often than not, we are talking about custom parts and custom prints. And so the content might be very, very unique. And so then the question is, how do we do visual inspection when the content is very unique, and you still have to figure out where the defect is? So one of the key challenge is then how how to tell apart the content from the defect. So today I'm going to focus more on the print inspection side. And um, so this is for the longest time, a lot of the inspection is done by a human observer and using a loop. And at HP, we have been looking at how to use machine vision to do print inspection. Actually, ever since HP started to make digital printers, and so so a lot of the classical computer vision is used, but we also have human observers essentially augmenting that process. So we use a combination of machine vision and human observation. And so when the printers are made, we have the testing process, and so this shows the testing process and how essentially we are printing a lot of test patterns, and then use computer vision algorithms to inspect these test patterns, and then decide on whether the print defects is present or not. And then we do very, very thorough testing of HP printers in all sorts of challenging environments, like very high humidity, high temperature, and then run it, continuously, make sure it performs well under all these different conditions. And for this kind of tasks, the classical computer vision can do very well. What classical computer vision finds challenging is how do we handle custom prints. And so this shows a inspection system, and that we're using, and so we use this to essentially grade print samples, and when it comes to custom prints, this is where really artificial intelligence comes in. So we deploy. So this is a product called WebPress. So it's called a page-wide WebPress. And it runs extremely fast, and so then it runs custom prints. So then the question is, in the field, how do we do inspection in this kind of situation? So so I'm going to kind of talk a little bit about our work in this area. And if we look at artificial intelligence, it has visual perception, speech recognition, decision-making, translation between languages. These are kind of tasks that typically associate with humans. And so we'll be primarily looking at visual perception in the inspection tasks that we're going to be performing. This, as everybody knows now, that it's really enabled by breakthroughs in deep learning. And with deep learning, we know that there are three kind of key factors. One is very large scale data set, one is better network models, and one is more powerful GPUs. So so with classical computer vision, we have been using that actually in HP for many, many years. And this typically is associated with print image quality, but also we have been looking at higher level computer vision tasks such as face detection actually in the early 2000s. And the use case is that we want to be able to detect faces in images so that we can render them really, really well when the printer is printing them out. So, so classical computer vision it usually have human designed features, and then use machine learning to make decisions based on these human designed features. If the amount of training data is small, it works pretty well. But the problem is it doesn't increase accuracy when we have more data. So so here we see that the pipeline is we have feature computation, and then we have classification. And these are relatively two independent tasks. So if we think about, for example, face detector, the way it works is that we have all these human designed features that we will use to run through the image, and then see how well the match is. And then we use a cascade classifier, sequence of cascade classifiers to reject non-face areas. And so we have been, as I mentioned, we have been working on traditional face detector since the early 2000s. And when deep learning comes along, of course, we will say, okay, so how do we replace our traditional computer vision techniques with deep learning? So so one of the really, really nice features about deep learning is that we can now have learned features. So we have the feature representation, and then we have the feature classification. It's an integrated network, and the features are learned. So if we think about a task like face detector, once a face detector is trained, then what we will see is that the first layer is really kind of detecting edges, and then the second layer start to detect face parts, like for example eyes, and then the third layer start to show face images. And so then the question is, how do we apply a principle like that on print defect characterization? So the objective we have is we want to be able to generate a print defect map with pixel level accuracy. So the challenge is that we have a huge lack of precisely annotated image data for training. And so if you look at this example images of some of the print defect, you will see it's very, very hard to annotate. Like, for example, streak defect, which is the first image on the left. It has a lot of pixels in the streak. It's not very regular. It's not very easy to kind of use a polygon to kind of indicate what are the pixels that belongs to the streak and what are the pixels doesn't belong to streak. And so the solution we have is to really use simulated artifacts for training data. And then we use real artifacts in printed and scanned images as testing data. So these are some of the examples where we do the simulation. So we use mathematical functions to create dot streaks and color bands. And then we also simulate the print scan effect. So if you have an image that's a digital image, then what does it look like when it's printed, and what does it look like when it's scanned? So we want to be able to simulate that that pipeline. And So then after that, we can start the training process. So we start with background images. So we have a very large database of background images. And then we add synthetic defects. And then we do resize and crop. And then we add print scan effect. And then we do augmentation. And then we apply semantic segmentation. So um, so the model architecture then is we have the printed and the scanned RGB image as the input, and then we have the original image optionally as the input as well, and then we feed it into our network, and we use a deep lab V3 Plus that's published by Google as our base network, and then we train it with our defect, synthetic defect. So then when we run the inferencing, we tried a couple of inferencing techniques. One is resized. So for a very large input image that's scanned, 7,000 by 5,000 pixels, we first resize it to a smaller image, and then we do the defect mapping, and then we upsample the defect map. Another technique we tried is patch based. So we divided up the original input image into many crops, and then we run the defect mapping on each of the crops, and then we concatenate the crops to show the original defect map. And so the first method is very fast because we are running through less data, but it's less accurate. And then the second method is lower speed, but it's more accurate. So then we ran the testing on real data. So we want to see if our simulation actually works, and so we run it on real data. So we annotate the images with real defects to pixel level, and then we tested 4 combinations. So we tested no reference and full reference, and then we tested resized image inference and patch-based inference. And so this table shows our result as well as the runtime. So you can see resized image, it runs very fast, 1.7 seconds, and the patch-based method takes a little bit longer. Interestingly, what we found out is the full reference, which has the original digital image as input, actually does not perform as well as no reference image. And so that was a little bit kind of a surprise for us. But we checked, and the result is correct. So our conclusion currently is that a no reference training method, the model trained with no reference images, and run inference with patch-based algorithm works the best. So these are some of the examples, the visual result of some of the examples. So we have the reference image here, we have the printed image here, and then we hand label it. And notice like this kind of bending is actually very subtle. So it's actually very difficult to label them. And so here's our labeling, and here is our result. So So we can detect very, very subtle streaks and bending with our models. We can also run the same thing. So here's example where we trained on spots. And then on the left image, we see the spots, real spots in a print sample. And again, you can see the spots are very, like there's no clear boundaries. It's not very it's visible, but it will be extremely difficult to detect with a classical computer vision because there's no clear edges. And the right side is our detection results with our trained model. Another effect we were detecting is the die-to-die transition. So for a very high-speed production printer, such as the web press, it's the printer is printed with kind of many cartridges all laid out in parallel, and so that each of the cartridges is manufactured independently, and so you can see that sometimes there are process variations. And our task is to be able to detect and correct those. And so the original image, you can see some very faint variations, particularly in the dark region. That's caused by the die-to-die transition. And then we label the ground truth, and you can notice that the ground truth labeling is actually not very consistent. The die-to-die transition is periodic, and the ground truth labeling, you can see that sometimes the transition is not very visible or not visible at all, and sometimes the human observer place a line in a non-transition area. And it's very interesting that our model can actually, you can see that the segmentation result is actually very good. We can detect essentially the periodic nature of this transitions, and through post-processing, we can actually get very accurate result. And with this, then we can further compensate that and reduce the visibility of the die-to-die transition. So, today I talked about our research in visual inspection, and in particular, I went into a deep dive with our print quality inspection. We also have done a lot of research related to automating a creative workflow. We call it HP Pixel Intelligence. And so, for example, we developed the software for AI photo organization and photo book creation. So if you have a lot of photos, we can find events, and we can find people, and then we can group people and group events, and then sort them into albums. And then we can also recommend photos for printing, and then produce the layout pages. And this could also all be done automatically. And another area that we have been looking at is super resolution. So if you have a photo that someone shared with you from social media, then the resolution and the quality would be both lower than the original capture. And so if you want to print a very large size, like a 16 by 16 poster, then the image quality will be very poor. And we developed a deep neural network with contextual features, so that the printout with enlarged image will be of very high quality. So we already have customers using our software for this creative workflow type of services. Okay, so so I'd like to thank you again for inviting me to Perceive 2020, and see if there are questions.
Sure, and we'd like to thank you for joining us and giving us that very informative talk there, Dr. Lin. We do have one question that came in from Usama. He was asking if there was any explanation maybe why NR was superior to FR. I think he was referring to the reference images. Was there some reason going on there?
Yeah, we have some theory, and our theory is that the print scan, so when we map the digital image to the print scanned image, we use a relatively simple process for doing that. And so if the printout, the real printout scan image, and the one that comes from digital image, and then going through our kind of simulated mapping, if there are still a lot of differences, then the neural network will not be able to really comprehend that kind of difference. And that probably is the result of the cause of the lower performance.
Interesting. Thank you for that. There aren't any other questions here. I had some of my own that kind of came up. If you're willing to indulge maybe one or two very quickly.
Yeah, sure.
I think I personally, and we see similar kind of use cases with automating visual inspection, QA, QC processes. I wonder from your experience, maybe two questions. Do you see some particular industries right now that maybe have some of the greatest opportunities to kind of transform and see the biggest value, number one? And then number two, what advice would you have to someone who's endeavoring to go ahead and actually start automating some of these processes? What are some of the pitfalls to avoid?
So we have been focusing on the manufacturing industry. It's a very, very large in size, and the kind of the variation in terms of the type of artifacts that needs to be inspected actually differs a lot. And so we see the opportunity there is really exciting and very challenging as well in the meantime. And then in terms of advice, I think what we found is this is a very, very how do I say it? It's not only a software problem; it's a solution problem that require hardware, software. So at HP we see this a really good edge opportunity and edge compute opportunity. So the solution itself requires capture, requires deep learning software, and requires hardware, storage, and the compute. So we are kind of really taking it from a solution perspective, and I think that's we believe that's important.
Yeah, I agree with that. That is what typically makes these kind of use cases so difficult, is that it's already typically a difficult data science problem, but then also typically a difficult solution and implementation problem too. So I agree with all that. I think we have time for this last question that came from Edward Schwartz here before we wrap up. do you maybe have any good examples or use cases, anything that you can speak to where computer vision was basically used in conjunction with analytics to find the root cause and ultimately actually change some kind of process, maybe either from some kind of direct work example or some kind of literature?
So that work is in progress. So I'm not ready to talk about it yet. I think I haven't seen much of discussion of this in literature, because this is such a practical and industrial problem, and there's not a lot of visibility in academia.
Yeah, I find that interesting, by the way, that it seems that literature doesn't want to focus on things that are deemed not, I don't know, not academic. I don't know. Interesting. I wonder if you find the same thing as well. We had one last question eke in here, so maybe you can address this one very quickly, and then we will, for real, wrap things up. So this one came from David Gill. He said, on top of the opportunities of deep learning, do you also study its limitations, especially in terms of privacy security? Do you focus on or have any thoughts on some of the limitations with deep learning?
Yeah. Actually, some of our customers actually choose our software because of the concerns about privacy. So I think the companies have become more and more kind of conscious of that. And if you use a cloud service, for example, you will be sending data to a cloud service, and if you can run the software at the edge, then the data would be entirely yours, under your control. So we found some customers actually choose our software because we don't use cloud backend. We have entirely kind of edge implementations.
Wow. Yeah, I know we're seeing the same thing here. We're excitedly moving towards and launching new edge kind of platform capabilities as well. So I want to just take a second to thank you again, Dr. Lin. I think that was really useful and great to kind of just put real business experience and show how it can actually be utilized, all this technology that we're talking about. So thank you again for your time. For everyone else, just want to reiterate, like I said before, I want to thank you all for attending firstly, and then to say that a recording will be made available of this session within 24 hours. Thank you all so much. Thank you, Dr. Lin.
Thank you.
Have a good one.